And welcome to our Forces of Motion study guide. I hope you had a little bit of fun there while you were doing the Down with Parachutes lab activity. Again, we were talking about the other day gravity and how gravity causes all objects on Earth to fall at or accelerate at a rate of 9.8 meters per second squared. You should have noticed as you continually made your parachutes smaller, it took a shorter amount of time for them to fall to the ground, indicating that the more air resistance you have, the larger the parachute, okay, the slower it was going to fall. And the first one, the largest parachute, probably even reached terminal velocity, and it allowed it to float and move in different directions. By the time you got to the smaller ones, they probably just fell straight down and were nowhere close to their terminal velocity. So again, just make sure that has been turned in or submitted, and we'll get going here with your study guide. Now, you are going to be having a test, everything we've talked about here from the laws of motion, okay, all the way down into where we talked about friction. Then we did momentum, calculating momentum and conservation of momentum, and finally gravity. So these are all the things that will be covered on your test. So let's just do a quick review here. I'll be typing in answers. You can follow along as I do that. And that should not be a problem for anybody. So let's get going. The three laws of motion. Who was our guy? Well, our guy, you guys should all know, is Isaac Newton. These are why they are called Newton's laws of motion here. So we have Isaac Newton, Sir Isaac Newton. His first law of motion is known as the law of inertia. Again, inertia is the resistance of an object's or resistance to change in an object's motion, and according to this and all, that means an object at rest will stay at, you guessed it, rest. It does not want to change unless acted on by what? What did we talk about? We talked about unbalanced forces. If all the forces acting in all different directions are balanced, okay, there's no one net force in any one direction. The object will simply stay at rest. On the other end of that is an object in motion will continue to move in a what? Straight line. So we're just going to get rid of that. This was supposed to be your answer. I think I have this messed up, so just let me fix that. It will move in a straight line at the same velocity or same speed, okay, unless acted on again by unbalanced forces. That is our law of inertia. Again, the reason it stays straight is there's no unbalanced forces. Okay, there's nothing pushing it left or right. It will remain at the same speed, okay, while it is doing that in the same direction. As I mentioned earlier, what is inertia here? Inertia is resistance to change in an object's motion. It wants to keep doing what it's doing. It is a property of all matter, and it depends on the amount of mass. The larger the object, the more mass it has, the more inertia it has. Larger objects are harder to get started moving, and once they get moving, they are harder to stop. So we can simply say here then that the greater the mass of an object has, the greater its inertia. So I'm just going to pause here for a second, make sure that all of you have had a chance here to get caught up. Okay, now we are going to move into our second law of motion. Our second law of motion here is called the law of acceleration. This is the one we have the equation for. According to this law, the rate of accelerating an object depends on the amount of force. Okay, force is one of the three things we will be looking at that is being applied to the object. And what else is going to be studied here? It's mass. That is where we get the equation. Then what we see down here, F, force, is equal to mass times acceleration. F equals m times a. Therefore, the rate of acceleration is always directly proportional to the force applied, and it is inversely proportional to the mass of the object. Okay? So, the rate of acceleration directly proportional to the force. If you push harder, it'll go faster. Okay? But it is inversely proportional to mass. Bigger things are harder to accelerate. Larger objects with the same force are going to not accelerate as fast. Okay, again, get caught up on those right there. And then what we are going to do is practice doing a few problems here. Okay, in which we find the mass, we find the acceleration, or we find the force. Okay, if we look at our first problem here, what would force be needed to accelerate again? A 10 kilogram crate at a rate of 3 meters. So we just set up, we have this equation right here, F equals m times a. So we're simply going to plug our numbers in. So we're just simply going to take 10 kilograms, and we're going to simply multiply that by 3 meters per second. And if we take 10 times 3, that's pretty easy. That is 30. Again, our units do not cancel out, so we end up with kilograms meters per second. And actually, it's meters per second squared, excuse me. So let me get that over here, meters per second squared. So it takes me a little longer to superscript these. And what you were supposed to remember then, a kilogram meters per second squared is a newton. So our final answer is 30 newtons. Now we can also, if we know what's going on here, figure out acceleration as long as we know the force and we know what the mass is. So in this case, we have a force of 8 newtons. Now, in order to work the problem and find your units, you got to convert this back to kilograms meters per second squared. And then after you do that, we're going to divide this. Okay, so I'm going to come over here and divide this by my 10 kilograms. Okay, you can see here I got kilograms on the top and on the bottom. So I just do my math, and I'm going to take 8 divided by 10. That is going to give me obviously 0.8. Again, kilograms are left out, so I am left with an acceleration in meters per second squared. Acceleration again is meters per second squared. That was from a while ago. And finally, if we know force and acceleration, we can figure out how big the object is. Again, I got to take my force, in this case 10 newtons. I'm going to convert that to kilograms meters per second, meters per second squared. Again, I'll simply do a division problem here, so let me underline that, and I'm going to go down here and place in my acceleration. My acceleration in this case is 4, and that should be meters per second squared. I think I have that wrong up there in the problem. Okay, this should be 4 meters per second squared right here. So on your worksheet, you might want to correct that. Okay, and then again, we do the math. We do 10 divided by 4. We get 2.5. We look and see what gets canceled out. It's the meters per second that gets canceled out, and we are left with kilograms. So that is how we calculate force times acceleration. Okay, so take a second here, or I'm going to take a second here and make sure that you get caught up. Okay, and this is in your thing, so if you get a little behind, you can always go back later. Now let's move on down, and we're going to talk about our third law of motion. Okay, the third law of motion is also known as what? Is known as the law of action and reaction. Okay, so what does action reaction mean? That states that for every force, there is a force of equal magnitude. That means it's the same amount of force, and this occurs in the opposite direction. Try to spell things here a little bit sooner, or better, sorry. Again, it's in the opposite, and I didn't even get close to spelling opposite right. Sorry about that. Let's make that an O. Okay, now if we look at these three laws real quick, and I'm going to kind of rush through these a little bit because I'm running out of time. If a rocket blasts off into space, what is that? Again, that is letter C. Okay, that is the third law of motion. The rocket pushes against the gas pushes back. A golf ball sitting in T until it's struck. Well, that is our first law. That golf ball has inertia. It doesn't want to move. So it's going to stay where it's at until a force is done. That boulder is harder to move. Okay, it has more mass. That's our second law. Okay, ball continuing around a frictionless track. Again, it will not change its motion unless acted on by an outside force. The first law. Ability to throw a baseball farther and faster in the air than a shot put. It's because there is less mass. Again, that is our second law of motion. And I messed up somewhere here, so let me fix that. Sorry about that. And again, pushing a wall in front of you and rolling backwards on a skateboard, that's called the wall pushes back with an equal but opposite force. So that is our third law of motion. Now I'm going to have to stop this video here. Okay, and then your sub will move into the second video, and we will start talking about friction.